Good evening. My name is Faith, and I'm one of the house managers here at Town Hall. On behalf of the staff at Town Hall Seattle, it's my pleasure to welcome you to tonight's presentation featuring cutting-edge research by UW students April Lowe, Doris Dye, and Lance Taconic. This is the final event in this year's UW Engage Science Series, and Town Hall is so pleased to have been able to offer this platform for these students and their important and engaging work. As we get underway, I would like to acknowledge our institution's stance on the unceded traditional territory of the Coast Salish people, particularly the Duwamish. We thank them for our continuing use of the natural resources of their ancestral homeland. We are so glad to have you join us tonight. Tonight's 3 presentations will run about 60 minutes in total, followed by Q&A. To submit your questions for the Q&A portion, please enter meet.ps/5-16 UW Engage or scan the QR code right now on the screen with your smartphone. We'll drop this link in the chat as well, and you can submit a question at any time. We'll try to get to as many questions as possible, and you can help by keeping your question concise. Also, a reminder that if you'd like to view the program with closed captions, click the CC button in the bottom right corner of the video player. Town Hall is adding new events and podcasts every day. Visit our website to view our calendar of upcoming events and sign up for our e-newsletter to receive updates as future events are added this season. Town Hall's work is made possible through your support and the support of our sponsors. As part of our Arnold G. Motulsky Science Lecture Series, this event is supported by Microsoft. Town Hall is also a member-supported organization, and I'd like to thank all of our members who are joining us. If you share the belief that our community is energized and inspired by considering questions of politics, science, and culture, I hope you'll consider membership too. There's information on our website. And now I'd like to introduce our first speaker. April Lowe is a genome sciences graduate student at the University of Washington and the Fred Hutchinson Cancer Research Center. In her research, she studies what happens in lung cancer cells when there are errors or imbalances in genes. By connecting changes in genes to changes in the cell's messaging system, she hopes to better understand and help treat this deadly cancer. Please join me in giving a warm welcome to April Lowe.
Thank you for that lovely introduction. Okay, let's see how this works. All right. Great. So I want to start this talk by inviting you all to take a deep breath with me. Deep breath in and deep breath out. That probably felt really good. And we have our lungs to thank for that. The lungs are a vital organ in our body that help take the oxygen we breathe in and distribute it across our body before taking the carbon dioxide our body generates and exhaling it back out. Unfortunately, the lung is also a site for cancer, much like other organs. And lung cancer is the second most prevalent cancer type in both men and women, behind breast cancer and prostate cancer. Unfortunately, lung cancer is also the most deadly type of cancer. There are over 200,000 cases of lung cancer a year in America and over 100,000 deaths a year. And when we think of lung cancer, we often think of smoking, and you would be right to think that. Many lung cancers develop because of a smoking history. However, there are many people, lung cancer patients, who develop this disease who have never smoked a single day in their entire life. So how does this happen in all these cases? And how can we treat them whether or not they are smokers? The answer lies in our DNA and changes in our DNA in cancer. When a patient presents in the clinic with lung cancer, the doctor may prescribe a standard treatment, and maybe for this first patient it works well and the cancer stops growing for a year or two. But maybe another patient comes in with a cancer that looks very much the same, and the same prescription is given to them, but this time the cancer continues to rapidly grow. And why this is often comes down to a change in our genes. So the question is, can we do better? Can we look at these changes in our genes before we give prescriptions to treat cancers and treat cancers better and with fewer side effects and for longer periods? So to answer this question, we first need to understand genes. And genes are blueprints for our cells to make proteins, which are the machines that our cells need to function day to day. So a protein might be a robot, like a robot machine. But cells have many proteins that do many different jobs. So if one protein is like your household robot doing day-to-day jobs, maybe other proteins are more like planes, which transport cargo across countries, or cars, which transport you to your friend's house, or a wind turbine generating energy, or a machine to generate the other machines and materials. So genes are the blueprints, and from these blueprints, cells can make these proteins. However, this process requires a very important intermediate step, a messenger. So the messenger takes the blueprints and tells the cell when and where to make the proteins. And these messengers are called messenger RNA, or mRNA. And you might be familiar with this term from the past couple years due to the COVID-19 mRNA vaccines. So what do these messengers have to do with the vaccines? The messenger RNA, the mRNA that is in our vaccines, represent a small piece of the SARS-CoV-2 virus, the virus that causes the COVID-19 disease. And this small piece of RNA tells the virus or our bodies how to make a small, harmless part of a protein that helps SARS-CoV-2, unique to SARS-CoV-2 as well. And when this mRNA is introduced into our body via a vaccine, our body makes these protein parts that are harmless, but because they are in our body can learn to recognize them and fight them, so that when the real thing comes along, our body knows how to fight it off. So this is the standard process. There's the gene, and that's a blueprint, mRNA, that is the messenger taking the blueprint to tell the cell what to do. And once the cell knows what to do, it will make the proteins that will do the thing. So what happens when there are changes in the gene? Maybe instead of the blue gene, we have a red gene. And so our blueprint is now red. And instead of our happy working little protein, we instead have a dysfunctional protein in our cell. And to describe this process a little bit more, I'm going to use another machine analogy, a plane. So genes are blueprints, and more precisely in our cells, they are made up of blocks on a string, and we can, and the messenger RNA and proteins will come from this. So imagine you are on vacation in somewhere in the middle of the country. It's all land, and you need to get somewhere. Your messenger will make copy the part of the gene that it needs, and this will be without the middle block, and make a regular plane to transport you around. However, what if you are, say, on the San Juan Islands, and you're surrounded by water? Then your messenger may include that middle part that has extra instructions to tell you how to make floats for the plane, and get you a seaplane to take you between the islands or back to Seattle. This is similar to what happens in our body. In our lungs, the mRNA may take one version of the gene to make a protein that is useful for the lung. And in our brain, it might take an extra part of the gene to make it more specific and more useful to the brain. And this process of picking and choosing alternative versions of genes through the use of the messenger RNA is called alternative mRNA splicing. So how does this play into disease? Sometimes that middle block is a block that we never want, that is broken, dysfunctional in some way. So in our healthy cell, our messenger RNA, mRNA, knows to cut that part out and not use it, and therefore make a healthy working protein. But in a cancer cell, they want that broken part, and so the messenger RNA includes it, and now we have a broken protein instead. And so in the context of cancer, you might have a healthy cell and a healthy lung that's generating these normal mRNA and normal proteins, but something changes and it starts introducing a broken part in the mRNA and making a broken protein. And because of these changes in the proteins, the cancer cells grow and become a lung tumor. And what we want to do is to design a drug that reverses this process. And so we want to tell the cells to stop making the mRNA that has the broken part and go back to making the regular version, and so that will also lead to making the normal protein. And I would like to remind you that the goal here is to prescribe treatments that are specific to the gene changes in our cancers. So to link the two ideas, the question that I ask in my research is what gene change causes what alternative mRNA splicing? And so that we can hopefully correct the alternative mRNA splicing when it has gone wrong, but leave it alone when it's doing fine. To answer this question, I work in the lab with cells on dishes, and I get to have fun stock photos taken of me. And so in the lab, we grow cells on plates, and on different plates, we will put in different versions of the gene. So here, for example, maybe on one plate I have the blue gene, and the other plate I have the red gene. And we let them grow for some amount of time, maybe 72 hours, and we look at them underneath the microscope. And so maybe we see that in the plate with the blue gene, the cells are growing healthily and look as we expect them to look. But with the red gene, they are growing more out of control and are starting to take on some cancer characteristics. And to link this to possible alternative splicing, we need to measure the pieces of the mRNA in each of these populations of cells. And to do this, we use a technology called next-generation sequencing, which uses a machine that looks something like this. And what this machine does is it takes the fragments of RNA or DNA and tells us exactly what they are. And because we know the exact identity of them, we can map them to the gene versions that we know are in the cell. So maybe some of them map to the version with only the gray blocks, but some match to the version with the red block. And when you match up all the data, you get what we call pile-up plots, where the height of those bars correspond to how many fragments match to that part of the gene. So for example, on the left and right sides, you have quite a few fragments matching to these two sections of the gene, but fewer fragments match to the middle section of the gene. And so we can count the mRNA pieces in each cell, and we can infer that when there's no matches in the middle, we are seeing the version with only the gray, and if we're seeing some matching in the middle, there's some mRNA with the red portion, and we can compare these across cells. So this requires a lot of work, again, stock photos, but now I'm at the computer, which is where I actually spent 99% of my time. And so looking at the data, we can first define what alternative splicing looks like with the normal gene and the cells that look healthy. And so here, in my data, I saw that there is some level of that alternative mRNA where there's the middle section. And we can draw a line and say, okay, this is the levels of mRNA that we expect when everything is normal. And this creates a healthy protein environment as well. And what happens when we change the gene? The change is not, it's pretty subtle, but I hope you can see that when comparing to the baseline that we drew with the normal, the blue side on the left, the data on the right side in the pink plots, there is more of the version of the gene that has that middle section. And this small change can make big differences in the cell and lead to the cell doing cancer things. And in the lab, we can do this experiment in multiple ways. We can change the gene in a different way and do the same test. And here we put another change in the gene and saw a similar increase in that in that version of the mRNA that has the middle section. So now we know that when there's a tumor and we see these, sometimes there's these broken proteins that are a result of a changed gene, and we can design drugs to convert these tumors back to normal by changing the alternative splicing process that these red genes cause, and hopefully successfully treat the cancer. And again, because we are answering the question, what gene changes causes what alternative mRNA splicing, we can know to only do this when there is that red gene that we have seen is what causes these different splicing patterns. And when there is the blue gene, we don't have to give the same drug, and maybe there's another drug that is more effective for that version of the gene. So in conclusion, lung cancer doesn't result only from smoking. There are many different causes, but whatever the cause of the disease, I hope my research and others will help in designing more effective drugs that are precise to the problems with a particular cancer, and in this way treat all the cancers and cure them and hopefully lower the number of deaths that are caused by lung cancer each year. So finally, I invite you all to breathe in again, breathe out. Thank your lungs for everything they do for you every second, every day, and treat them well. And I thank you all for your attention.
Thank you so much, April, for starting us off and for incorporating robots into a presentation about lung cancer. That was amazing. My name is Kevin Bishop. I'm the instructor for the Engage course at UW, which is the course that all of our presenters tonight are in, learning about science communication. And it's my pleasure to introduce our next speaker of the evening, who is Doris Dye. Doris is a fifth-year student in social psychology at the University of Washington. Her research focuses on how historical representations of Native Americans shape non-Native individuals' misperceptions of Native Americans, and how such misperceptions have downstream negative consequences on Native Americans' well-being and lived experiences. Please join me in welcoming Doris.
Thank you, Kevin, for the introduction. So let's take a moment to think about the last time you saw a Native person in movies, TV shows, or video games. How was that Native person depicted? The Native character is very likely a historical figure, like the images here, wearing feather headdresses, buckskin clothing, war paints, carried tomahawks, bows, and arrows. In fact, when looking around us, we almost exclusively see historical representations of Native Americans, while rarely see any modern ones. For example, only up to 0.4% of media representations portray Natives, most of which are historical. Across 50 states' school academic standards, among the very few references to Natives, only 13% portrays them in a post-1900 context. Even in social science research, among all the published papers on stereotyping, prejudice, and intergroup relations, only 0.5% mention Natives. And finally, if you search Native Americans or American Indians on internet, you will find 95% of the first 100 Google images are again historical portraits, as illustrated by this very recent screenshot taken from Google Images. So it is not hard to imagine that for an average non-Native individual, surrounded by all these historical representations of Natives, while lacking contact with any modern ones, it is almost inevitable for this individual to misperceive Natives as people of the past, who only exist in the history and have completely vanished from today's world. And I refer to this misperception as the Native past stereotype. However, all these historical Native representations do not reflect the vitality of the Native population at all. According to the 2020 census data, 9.7 million Natives currently live in the US, which is larger than the total population of Washington State, which has around 7 million residents. More importantly, the Native population continues to grow yearly. So this chart plots the Native population growth over years between 2000 and 2020. You can see the trend, you can see a very obvious upward trend here. So there's an urgent need for us to understand how the inaccurate Native past stereotype can impact the lived experience of Natives and many generations to come. So one downstream effect of the Native past stereotype that my research focuses on is that it can hinder the efforts to advance racial equality. So one premise of recognizing racism is knowing that there is a target of racism. If Natives do not exist, then how can any discrimination or injustices occur to them? In other words, holding the Native past stereotype can allow people to minimize the extent to which Natives experience racism. There are some evidence out there suggesting the discrepancies between the actual racism Native go through and what non-Native people believe about Native experience. In reality, natives face injustices and inequalities across all consequential domains. For example, natives are more likely to be killed by law enforcement than other racial or ethnic groups. Natives also experience extremely high rate of sexual violence, such that 1 in 2 Native women and 1 in 4 Native men have experienced sexual violence at one point. And natives constantly have lower median household income compared to the total US population. As a result, 75% of natives say their group faces discrimination. Surprisingly, when asking non-native people, only 1/3 believe so. Of course, there are a lot of reasons behind this minimization of native racism. Here, I theorize that one explanation is the endorsement of the idea that natives are people of the past. If people cannot see natives' existence and racism against natives, then they will also see no needs for any measures or policies serving this seemingly non-existing group and a non-existing cause. That is, holding the native past stereotype can subsequently lower people's support for policies designed to address native injustices. So why is this process alarming? From large-scale social movements such as Black Lives Matter and #MeToo, we have learned that rectifying injustices against a group of people require engagements from a broader society, not just from the disadvantaged group itself. If we are unable to motivate non-natives to engage in native issues, then we're forcing natives to carry all the burdens on their own. So recognizing the potential detrimental effects of the native past stereotype, I started a journey tackling this issue, along with my team led by Dr. Stephanie Freiberg, who is a notable Toledo psychologist scholar. But at the very beginning of my journey, a challenge halted my entire research project. That is, I cannot detect the stereotype itself. So we psychologists often rely on self-report measures to get insights into your inner mind. We may ask you whether you felt a certain emotion or endorse a certain viewpoint, because we believe that the person who knows you the best is yourself. So one good example of self-report measures is a Myers-Briggs type indicator test. In my study, I asked people to rate the extent to which they agree with a series of statements saying natives no longer exist. So scores below the neither agree nor disagree at midpoint will suggest that people do not have or have very weak native past stereotype, while scores above the midpoint will suggest the opposite. And I expected to find most non-native people scoring above the midpoint. However, in my previous study that had more than 3,000 nationally representative non-native participants, most scores clustered around 2.1, which is way below the neither agree nor disagree midpoint, which is 4. In other words, most participants rejected statements such as native peoples are not around anymore. And this pattern has emerged again and again across many studies. So I was very discouraged by these findings, and at some point even thought my whole career was going to end, because it seems like my research was based on a false phenomenon. But as I took a deeper dive, I realized that scores below the midpoint do not necessarily indicate an absence of the native past stereotype. Instead, non-native people might be hesitant to or not wanting to endorse the idea that natives no longer exist, because when we deliberately considering this idea, people can either recognize how implausible or ridiculous this idea sounds, or they may think saying natives have vanished is politically incorrect and will make them look racist. Instead, I argue that the native past stereotype might be an implicit bias instead of explicit one. So what is implicit bias and what is explicit bias? To take an example, let's look at this photo. Which baby do you think is a girl? So for many of us, our instant judgments is that the baby in the pink clothes and with a pink background is a girl. But when we take a minute to think about it, we may say, wait a second, it is possible that both babies are girls, given that they basically have the same faces, and truly color has nothing to do with one's biological sex. So in this example, the idea that instantly popped into our mind, that pink is for girls and blue is for boys, is an example of implicit bias that exists outside of our conscious awareness and can be retrieved effortlessly and unconsciously. While the idea that comes later, that color is not an indicator of sex or gender, is explicit. So explicit bias is the conscious type that people deliberately think about and report. Also, you can hold an implicit bias even if you disagree with it. In other words, implicit and explicit bias can contradict each other, again illustrated in this example. Furthermore, implicit bias reflects life experience and cultural environments. So in this case, regardless of our personal beliefs or personal values, we most likely still hold the implicit associations between pink and girls and blue and boys, because we live in a society which is infused with such associations, as we see in toys and children's clothes. So given the differences, measuring implicit bias and explicit bias also require different methods. So the self-report measures that I just introduced to you a couple slides ago measures explicit bias because people are fully aware of them and can report accordingly. But since most people are unaware of their implicit bias, how do we measure them? We need a test called implicit association test, also known as IAT. So lucky for me, a website called Project Implicit invited my team for a collaboration to create a native-focused IAT last year. So people can go onto this website and take tests to learn about their implicit attitudes toward different social groups, including Black Americans, Asian Americans, transgender people, etc. To date, over 20 million people have completed studies on this website. Data from this website has also been cited in many mainstream discourse, including Congress hearings. So to understand how an IAT works, let's together do a shortened version of the IAT I developed, and then I'll explain the logic. So at the very beginning of the test, people see a table like this that contains all the categories and words that they will encounter in the test. And people also learn the correct category for each word. So in the initial combined task, you will see two categories that are pairs between targets, in this case, white Americans versus Native Americans, and attributes, in this case, present versus past. Then you will see a word, for example, Homa, pops up in the center of the screen. Your task is to decide in a split second how to categorize this word and press the corresponding key. So you recognize Homa is a Native American name. In this case, you are going to press I to put it into the native or past category. So let's try to categorize words together and try to do it as quickly as possible. Scott. So we are going to press E to put it into the white or present category. Vanished. We'll press I to put it into the native or past category. And then in the second combined task, the pairings are reversed, such that instead of native or past, now we have native or present. So let's try to categorize words again. Dead. So now you recognize it's a past word, but this time, instead of pressing I, you need to press E to put it into the white or past category. So the guiding idea behind the IAT is that concepts that are linked in our unconscious minds are much easier to categorize together compared to concepts that are not linked together. So when we're forced to make judgments in a split second, we resort to using our unconscious minds. So concepts that are linked together are referred to as the congruent combinations, in this case, the native-past pairing. And the concepts that are not linked together are referred to as the incongruent combinations, in this case, the native or present pairing. The IIT uses an algorithm to calculate the differences between how fast people make correct judgments in each combination task. If judgments are made faster in the congruent combination task, then we are going to have a positive IIT score, indicating stronger associations between natives and the past. In contrast, if judgments are made faster in the incongruent combination task, we will have a negative score, indicating stronger association between natives and the present. Finally, bigger scores indicate stronger native past stereotypes. So nearly 3,000 non-native Americans took the IIT test, and this plot shows the percentage of participants receiving each score. 0 indicates no association between natives and the past. In other words, no implicit stereotype. And bigger positive scores indicate stronger native past stereotypes. So you can see here most participants' IIT scores clustered above 0. In fact, 83% of our participants received positive scores. In other words, the vast majority of the non-native participants hold native past stereotype to some extent. So now let's compare their implicit stereotype to their explicit ones. So I measured explicit native past stereotype using the same self-report measure that I just showed you, in which I asked them to rate their agreements with items saying natives no longer exist. And the x-axis contains the self-report scores indicating the explicit stereotype, while the y-axis contains the IIT scores indicating the implicit stereotype. On both axes, larger values indicate stronger stereotypes. So I will show you data points from all the participants, and I also split the plot into four quadrants based on how high or low the implicit versus explicit stereotype is if a point falls into the quadrant. So here we can see most points fall in the top left quadrant, indicating most participants reported high implicit native past stereotypes, but low explicit native past stereotypes. In other words, non-native people can indeed unconsciously perceive natives as people of the past. So now that I find a way to capture the native past stereotype, I can finally move on to my main argument, that this stereotype has negative implications for racial equality. So to do so, I assessed the extent to which people minimize racism against natives by asking them to rate their agreements with items such as Native Americans have an equal chance of success as white Americans. I also measured people's support for policies aimed at addressing 4 types of issues that are most urgent for Native communities, including teaching accurate information about natives at schools, promoting accurate representations of natives in media, rectifying resource inequality, and protecting sovereignty rights. So first, let's focus on the first half of my theorization. In this plot, on the x-axis, we have the predictor, in this case, the implicit native past stereotype. And on the y-axis, we have the outcome, in this case, minimization of racism. Each point in the plot represents responses from one participant. And finally, the red line shows the overall trend of the relation between the predictor and the outcome. An upper line indicates that as the predictor increases, the outcome also increases, while a downward line means as the predictor increases, the outcome decreases. So you can see here the line is going up, meaning that the more people implicitly perceive natives as people of the past, the more they minimize racism against natives. Now let's move on to the second half of our theorization. So we still have implicit native past stereotype as the predictor on the x-axis, but now the outcome on the y-axis becomes the policy support. So you can see the line is going down, meaning the stronger implicit native past stereotypes people hold, the less likely they support policies addressing native injustices. Interestingly, when we take minimization of racism out of the equation, the line turned from going down to being almost flat. In other words, without effects of minimization of racism, changes in people's native past stereotype have nothing to do with the extent to which they support policies. This means that minimization of racism is the reason that non-native people who hold strong native past stereotypes are less likely to support policies designed to address native injustices. Just a short summary of what I have found. Non-native people on average implicitly or unconsciously perceive natives as people of the past. And non-native people who hold strong native past stereotype also shows lower support for policies addressing native injustices because they are more likely to minimize racism against natives. Mainstream society constantly misrepresents natives as people of the past, erases their contemporary experience, and denies them effective means of rectifying inequalities and improving lives. However, natives are not frozen in time. They have survived through historical genocides and forced displacement and continue to thrive in the face of ongoing injustices. Today, Native peoples are pushing back against historical representations of their group by actively pumping out their own stories and their own narratives. The onus for change, however, does not solely fall on the Native communities. If you want to make some changes, the first step can be as easy as streaming a TV episode by and about Native people with your family members and friends tonight, such as Molly of Denali and Reservation Dogs. Thank you for the attention.
Thank you so much, Doris. And our final speaker for tonight is Lance Taconic. Lance is a second-year bioengineering PhD student studying how to better deliver drugs using ultrasound. His research explores how ultrasound can increase temperature inside cells, weakening them and assisting drugs to better penetrate those cells. Please join me in welcoming Lance.
Started. All right, thank you all for having me. So I have some bad news for you. Your house has a pest problem. As you were getting ready this morning, making your lunch, you unfortunately noticed some little critters scurrying across your counter and you think, all right, I need an exterminator. So you look online and you find an advertisement for my company, which is saying we have the latest and greatest in bug catching technology. You think that sounds good enough, so you schedule an appointment. I arrive shortly afterwards and say, don't worry, I've done this a million times, happy to add another success story. And I proceed to pull out a flamethrower and put a blindfold over my eyes. And before you have any time to protest, I'm rushing inside into your house and looking for those bugs. Now, as well-intentioned as I am, knowing even if the bugs are in your kitchen, I'm gonna set your whole house on fire. And while this may seem like a silly example, this is unfortunately pretty close to what patients that are undergoing chemotherapy have to go through, where their home is their body and they've unfortunately contracted some type of cancer. The treatment is chemotherapy. It is effective, but it can be overkill. So the goal today is to see if we can improve this technique and make a more targeted version. But before we can fix the problem, we first have to understand what exactly we're looking at. So, what is chemotherapy? Well, to set the stage, since we're on one, there are about 1.8 million new cancer patients every year in the US alone, and 75% of that group is eligible for chemotherapy. It's a very common drug and it's a very common treatment of cancer treatments. Why? Well, it's very effective at attacking cancer. And the main reason for that is it's attacking fast-growing cells, which is one of the main characteristics of cancer. And on average, this takes about 5 months to do, where you take one treatment per month, get it confirmed in the hospital how you're responding to your treatment, and hopefully go into recovery once your cancer is gone. Unfortunately, there are some problems with chemo, and that, one of the biggest, is the collateral damage. Cancer is not the only fast-growing cell in your body, so things like your hair and skin are also fast-growing and can suffer damage from your chemo treatment. And more importantly, your immune cells, the cells that help keep you healthy and alive and defend you from viruses, are also fast-growing and can be damaged. And all of this is what leads to those long recovery times of 1 month, as your body needs that time to recuperate and get ready for another round of chemo. And even if everything goes correctly and the chemo finds its way to the tumor or the cancer site, you have problems even penetrating the tumor. Oftentimes we think about a tumor as this blob that's inside your body that just we want to get rid of, but a more accurate representation is a shelled area that has a lot of walls that we need to break down and get through. It's a complicated environment on the outside of a tumor because it does not want to die. Its goal is to expand and take over your body. So when the chemotherapy arrives, it has to break through all of those walls, and this is why we're also suffering from all these side effects, as we need sometimes higher doses to have enough of the drug to push through the tumor and start to break it down. So obviously, there are issues here, hence the flamethrower. And our goal is to turn this flamethrower, which can be overkill, into something much more targeted, much more specific to the problem we know we have, which is a tumor inside your body, and turn into something like bug spray. So how do we do that? Well, the main principle that we're using is heat, because to cells, heat is equivalent to stress. More specifically, cells will actually become stressed when there's a mild temperature increase around them, kind of like experiencing a fever. It's not fun. They start to shut down, minimize their interactions to conserve energy. And to us, as human beings, this temperature range is not too bad, 4 to 18 degrees Fahrenheit, kind of like stepping out of the shade of a tree and into direct sunlight. But that temperature range is actually enough to start to shut down these cells. And the good thing here is that cancer is not an exception. They also become stressed. So if we can utilize this heat stress phenomenon, what we're aiming for is you have your tumor taking cover under the shade of the interior of your body, where we're regulating all our temperatures. And what we want to do is shove it out into the light of day and start to heat it up, because what will happen is once it becomes stressed, all of that complicated environment on the outside of the tumor will start to break down, weaken, and the repair mechanisms inside the tumor will also get slowed down or stopped, which makes it perfect conditions for chemotherapy to attack and destroy our tumor. So now the question is, how do we generate that heat? We can't just heat up your whole body, because that wouldn't be fun for patients to get a very high fever. So we can actually do this with ultrasound. And this is the technique that I'm developing, which I'm very excited to present today. But when I first mentioned ultrasound, you might think of something like this, a black and white baby picture, very cute. A lot of people have experience with this. But this, by design, does not have a lot of heat generated. We clearly don't want to heat up a baby while it's in the womb. So we're not using this parameter space. Rather, we're using new techniques, but the same equipment to do new useful things like heat-based therapy. So rather than thinking about a baby picture, I'd rather you think about a magnifying glass in the sun, where the sun produces solar energy that comes down to the earth. You have a magnifying glass somewhere in your hand. That magnifying glass has a lens, and it is able to focus that light to a point. And much to the horror of some parents, a nasty kid can use this setup to burn something like an ant. And we can use a similar setup to this. Instead of trying to burn a poor ant, we can target something in a patient's body like a tumor, using a very similar setup with ultrasound. So instead of the sun, we have sound energy. It's still energy. We take our ultrasound probe, which has a lens. That lens is able to focus our sound to a certain spot, and if we aim everything just right and we know where the tumor is, we can generate that heat, create that stress response, and start opening it up to improving chemotherapy. So we have our basis, we have the technique, we've pretty much solved that heat stress problem, right? Job done. Thank you for coming to my talk. Well, I wish it was the case. When we go to put it into practice and you line up your ultrasound probe with the tumor, you're ready to go, you turn on your heating mode, you get a tiny little treatment area. And unfortunately, this is not enough to get the full stress response that we need. In order to fully cripple this tumor, we need to do multiple treatments spread across the area of the tumor. And this comes with a whole host of different issues when you start to move off of one treatment area and move to the next. Where you were just treating starts to cool off and may start to recover and repair while you're trying to do treatments around this entire tumor. And all of this is on a micro scale. So this is ideally done by someone in the clinic holding a probe onto a patient. The patient is breathing. Lots of complications, very difficult to aim. So not realistic to use this method. Ideally, we just have a single treatment. You turn the probe on, it treats the entire tumor, job done. Right now, we can't do this, but we can actually use another part of our ultrasound arsenal to help get this single treatment, and that is with something called microbubbles. So microbubbles are pretty similar to the bubbles that you may have played with as a kid, where instead of them floating through the wind, they are small gas balls on a microscale, so they're about the size of your red blood cells, and they are actually safe to inject into your bloodstream. So often we use these microbubbles as a way to improve our ultrasound images. We can inject it into your bloodstream, so wherever your blood is, the microbubbles will follow, and if we're looking for where the microbubbles are on our ultrasound image, we know where your blood is. So since we're not doing imaging, we can use that same setup of letting the bubbles flow through your blood, arrive at the tumor, and they actually have some very interesting interactions with ultrasound if you pick the correct settings that complements our heat goal. And the most important one I like to call the kindling effect. So similar to how you want to light a pile of logs to kind of warm yourself up during the winter months, if you're just trying to light the logs with one match, you're not going to be very successful. You need a lot of energy, or you need a very big fire to heat up that entire pile. So a better method is to put together some kindling, either crunch up newspaper or little twigs, scatter them around your log pile, light in different places, and the idea is collectively those little fires will heat up the logs and start your actual flame that you're interested in. So here, microbubbles are our kindling. We do the same setup of inject the microbubbles, flow them through your bloodstream, allow them to arrive at the tumor, line everything up as we did before, and what turns out is that when you turn on your ultrasound probe and do your little heating, all those little microbubbles will act as a little kindling pile, and all that heat around the tumor basically acts as a collective to cover wherever that tumor is. So we've effectively turned on our probe once and covered the entire tumor. So in this case, yes, job is done. We've done what we sought out to do. But we actually have a second effect, which I like to call the drill effect, which will be very helpful for improving our chemotherapy, where we have the same setup, but rather than looking at how much heat we're generating, we look at what the bubbles are doing. And initially, when you turn on your ultrasound beam, the microbubbles will actually start to vibrate. They'll expand and contract. And while they're doing that, they're basically creating elbow room and pushing on the liquid that's around them. And for the microbubbles that are close to the surface of the tumor, as they're doing this pushing and pulling motion, they will actually rub and pull against the outer layers of this tumor. And what ends up happening is you start to poke some holes into the outside of the tumor. So not only are we treating the entire area with our heat, but we're also starting to break down some of the outer layers and opening up some channels, which is perfect for delivering chemotherapy faster. So if we put it all together, we inject our chemotherapy and microbubble cocktail into your bloodstream, all pretty standard stuff. It eventually makes its way to the tumor. You line up your ultrasound probe, turn everything on, and you get two big effects. First, that heat treatment, we're covering the entire tumor area. It starts to break down that complicated structure, and it can't repair itself, so it's been weakened. Then we have the secondary stage of the drilling. We're poking holes in the outside layer, and now we have brand new avenues that are perfect for our chemotherapy drug to rush right in and just attack from the inside rather than spending energy pushing its way through the walls. But there's something that I haven't addressed yet, and that's how did the chemotherapy get there? We still have that issue of chemo around our entire body and potentially attacking those cells that we don't want to attack. So how do we protect the body from chemo? And the answer is actually pretty simple. It's basically put chemotherapy in a box and wait for us to let it out until we want it to. And the way to do this is essentially put a heat-sensitive shell around our drug. So rather than having it float around as it normally likes to do, we can encase our chemotherapy drug in a shell. And it's looking for a certain temperature to break open. And normally this temperature is set to higher than your body temperature. So we can just encase our chemotherapy drug, put it through your bloodstream as normal. It won't open, but if it encounters something like our high temperature area where the ultrasound probe is, you'll get that heat spike signature. It'll then say, all right, it's time to open up, and it releases our chemotherapy drug. And what's nice about this is you're only releasing chemo where your ultrasound probe is, which means only at the tumor site. So everywhere else, chemo technically does not exist, and it shouldn't attack those extra cells. So our actual full process is we start with a protective shell, line everything up, turn on our probe, and our first step is then actually to release the chemotherapy drug. Then it's business as usual. We break down our tumor environment, weaken it, poke holes, let the chemotherapy rush in. So we've solved our flamethrower problem, finally. But there was still that weird issue of the blindfold. Although we have fixed the flamethrower, we have our bug spray can. If you think about being blindfolded while to treat bugs with a spray can, you might actually be less successful than the flamethrower in the first place. So there was no point in doing all this work for nothing. But there's actually an easy way to remove this blindfold, and it's something that I kind of skipped over at the beginning of this presentation, and that's the system we're using in the first place. Initially, I asked you to consider that ultrasound is just a therapy system, and we're using it that way now. But if we go back to our roots, and that ultrasound is also imaging, we can find a way to pair both of these modes to work in tandem so that we're delivering the therapy and weakening the tumor and enhancing our chemotherapy, but we're also using imaging so that we can line up where our transducer is and know exactly where the tumor is, so we know that we're lined up properly and we're actually treating what we want to treat. But there's a little bit of a complication, like everything in this presentation, that we need to address, and that's that both of these are sound-based, and therefore they can't operate at exactly the same time. It's kind of like if you're trying to play two songs at exactly the same time. It's going to sound like a bunch of noise, and you don't know what's what. You don't know which chorus aligns with which melody. We can't have that because we need to know that we're delivering the right amount of therapy and the right amount of heat so that we can weaken the tumor and make sure that we release our chemotherapy drug. This is now vital. And at the same time, we need to have a good image so we know that we're aiming at the right spot and that the patient is responding properly to this. And the way to do this is also pretty straightforward. Rather than playing two songs at the same time, you play one song, turn it off, start the next song, turn it off, and you go back and forth like that. We can do the same with our ultrasound. The key here is just making sure that we time the different modes so that we get the maximum effect from each. So we can get a starting condition where we're lining up our ultrasound probe with the tumor. And if I go back a slide, something we would look for in an imaging scan is something like that black void at the top of the image on the right. If there's no bronze or orange color, this is tracking where our microbubbles are. And since the microbubbles are in our blood supply, if it's a black part of the figure, that means there's no blood there. And if we're heating a tumor, that means that that's probably where our tumor is, so we can align everything to that spot. So we would scan, make sure we're in the right area, and get ready to do our therapy. And we only need about 50 milliseconds, which is a very brief window of time. I think it's about a third the speed of what it takes for you to blink your eyes. And that's enough to just get a snapshot. We just want to see where we are and that we're good to go. Turn off our imaging, turn on our therapy, and leave it on for a long time. And the important thing here is time. You need enough time to deposit enough energy at the site so that we can break those shells, get a high enough temperature, and start to weaken the tumor. And then we can check in briefly afterwards, see that hopefully we've released our chemotherapy drug, and then just alternate back and forth where we're delivering therapy, heating the tumor, and monitoring it and seeing how things go. Hopefully, we see the last image in the patient that the tumor has broken down and chemotherapy has made its way inside. But if we don't see this, this is also useful information, as it means the patient is not responding to the current drug or the current treatment, and we'll know right then and there if the patient needs to switch up their treatment parameters, and we can also inform the doctor of any complications. So the final product, we've turned our flamethrower into a can of bug spray and taken off the blindfold. So what? Well, the first big news is that we've reduced that overall collateral damage, and that's thanks mainly to that shell around the chemotherapy drug. Since we're relying on heat-based techniques, we have a heat-sensitive shell, and that protects the body from chemo unless we want to release it exactly where we want to release it. We've also reduced our patient recovery time, because now we're weakening the tumor. The drug is able to penetrate much faster, and we can use less chemotherapy overall, potentially, since we're only releasing it at one site. And since it doesn't need to break through the walls, it can act from the inside and hopefully break down that tumor faster. So that means treatments can happen on a shorter time scale, and since we have less collateral damage, patients need less recovery time to recuperate from any of that side effect damage. And finally, we've also improved our patient information. Since we're imaging at the same time, we know exactly how patients are responding to our treatments. Normally in these cases, patients will have to get imaged anyways, and this can often mean like 3-hour waits after your treatment. So if you can imagine feeling weak after your chemo treatment and then have to wait a couple more hours in the hospital just to get a nurse or an imaging system to make sure that you're actually removing the cancer from your body, only to find out you may not have removed it. We can find out while we are treating the patient and not have to subject them to extra pain and suffering. And finally, it wouldn't be research without more to do. So the exciting thing about this technique that we're looking at is that it can enhance any drug, technically. We're not relying on any of the chemistry or the specifics of chemo. We're just improving how it works. So if there's any type of drug that is having difficulty getting into a patient, or if a patient is allergic or resistant to a certain kind of drug, we can use a technique like this to soften up a cell, because we're not fully destroying it, and allow a drug to fully penetrate certain areas of the body. So more exciting stuff to come, hopefully. But for now, thank you for your time, and I've had a great time talking to you all.
Wonderful. Thank you so much for our three great presenters for today. And it looks like we have a whole bunch of audience questions, so thank you all for submitting them. And we'll just get started here. So the first question is for April. And the question is there only one, quote, red gene in lung cancer?
No, definitely not. There are many different genes. There are some that are more common than others. So there's one gene called KRAS that causes a lot of gets these bad changes that causes a third of lung cancers, and then another called EGFR that causes 10%, and there's 40% of lung cancers that we don't even know what gene is causing them, but we know there is one of these red genes there.
Awesome. Thanks, April. And then this question is for Doris. And it says, can you recommend any entertainment such as TV, movies, or books that represents or showcases Native Americans or Native American characters that you enjoy?
So Reservation Dogs, that's the one I mentioned at the end of the slide. It's actually a great TV show you can watch on Hulu. Hulu didn't pay me any money. It's not an advertisement for Hulu. And actually, interesting story. So we collaborate with a Native organization where they have a lot of connection with the media industry. So Reservation Dogs, there's actually a lot of efforts that pushed forward by that organizations that are backed by research from my team. So I think that I have some personal connection with that show. That's why I highly recommend it. But if you have kids, you should watch Molly of the Molly with them. That's the first ever cartoon featuring Native Americans. Yeah.
Cool. Awesome. Thanks, Doris. And then here's a question for Lance. And it says, could you speak to your technique and pump cells that are resisting the chemo?
And what was the pump cells?
Pump cells?
Pump cells. Yeah, so there's no pump cells in the current technique. I guess I kept it kind of vague, but essentially the initial research has shown that just increasing the temperature reduces the blood flow to the tumor, but actually increases the drug uptake generally to the interior of the tumor. So we're kind of combining this effect and hunting down this temperature target range where you have just enough heat to still have some blood flow, but enough heat to increase that drug uptake. So it's this subject of study. It's still not super well understood, but exciting to explore.
Cool, thank you. And then here's another one for Doris, looks like. And it says, is there evidence that IAT scores reflect expected results? For example, if you compared IAT scores between natives and non-natives, would natives score lower?
This is a very interesting question. So first of all, we did want to compare native scores with non-native scores. However, unfortunately, we did not get that many responses from Native Americans, so which kind of reflect kind of like the miscommunication between Native community and the mainstream community. And I think regarding how Native people will score on the IET, I think it kind of depends on how they internalize the stereotype, right? So I will imagine for a Native person living on the reservation where they're in contact with other Natives all the time, I think they're going to score very low on the IET. Because as I mentioned, implicit bias kind of reflects cultural environments. But maybe for a Native person who live in a suburb or in a city where there are not a lot of Native people around, they may be surrounded by, saying, just non-Native people, then in that case, I will expect maybe they will internalize the Native past stereotype and even score at the same, around the same level with non-Native people. But it's kind of like open to question. Yeah.
Sure, thank you, Doris. And then here's one for April, and it says, what has been the most surprising thing you've encountered in the lab?
Good question. So one thing I didn't quite talk about is that we looked at a bunch of different genes and how they affect alternative splicing, and we were expecting to see some that were genes that are known to be involved with RNA already, but instead it was the most common gene, and it's regulating the RNA of something that will regulate itself. So it's like this circular loop, and I'm not entirely sure what it means yet, but it is definitely interesting, and it's definitely showing that like cancer finds ways to just like amplify itself.
Great, thank you. It's good that we don't understand everything, because then we're all still employed. This is a question for, oops, and I lost it here. Okay, a question for Lance. Is there a visual, real-time effect on tumors that you can see with the ultrasound when you are applying chemotherapy and heat?
Ideally, yes. So one thing we could do that would improve the visualization of this is to pair a dye with the chemotherapy agent. Since we're using usually contrast imaging to look at these things. So if there's a dye associated with this, you would basically see the inside of, if you think back to that image I had of the black void that was on that mostly orange picture. If the dye was red, you would see red seeping into that black void. You would know that then, since that dye is only in the chemotherapy capsule that we've designed, that you now have delivered the drug successfully, and you can kind of quantify how much of that dye has arrived, and therefore how much of the tumor should have broken down based on the chemotherapy concentration in there.
Great, thank you. Here's another one for Doris. What impact does continued equivocation around Columbus Day or Thanksgiving have on the perception that natives exist in the past?
Okay, so this question is kind of multifold. So first of all, how we celebrate Columbus Day and Thanksgiving now is not just an omission of the history, but more is kind of an extortion. A distortion. Because when you look at, for example, Columbus Day, when you look at the actual history, Columbus is one of the most brutal settler in the whole world. And he was actually imprisoned before he died. That's how brutal he was. But when we celebrate Columbus Day, we're saying Columbus was a good man and nothing he did actually happened. So this kind of sends out two messages to the Native communities. First is we deny the actual history that happened to them, and second of all is we kind of pretend that they don't exist anymore, right? Because we're pretending they're not part of the whole society. So the continuation of celebration, Columbus Day and Thanksgiving are very problematic, and we actually have attendee today, Terrence. He actually had a paper on the negative effects of keeping Columbus Day. But the short take is these kind of holidays deny the actual history and distort the actual history, and will have very long-term negative effects on natives' well-beings. Mm-hmm.
Wonderful, thank you. And then here's for April. It says, how do you account for interrelations between red genes and other genes? How well can the influence of a single gene be pinpointed?
Yeah, that's a great question. And the answer is that it is hard, but we have methods to essentially change the levels of the, different genes at the same time, so we can knock down or get rid of the red gene, but maybe there's another, I don't know, purple that is still there, and we'll see if the effects still exist. Do the opposite, red and purple, not red but purple, and then red and purple, and compare the differences. So I have, actually one of my lab mates is doing a project that does these kinds of comparison studies.
Cool, thanks, April. This was one for Lance. The question says out of left field, so I'm excited about it already. It says, I'm curious about ways you've explored sound. I've heard cells make noise. So do tumors have a distinct audio signature? Does knowing that allow you to target it at all?
So everything in your body will scatter sound. There's no tumor profile. I guess the profile of sound would be how we create the image that I saw, that we've shown on the slides. So we couldn't use sound that way. There's definitely weird things you can do with sound. I know there's fun things like sonoluminescence, where if you use sound to excite something, it will sometimes produce light at very high pressures. So there's definitely weird things there that we can do with sound. But in this project, the exciting thing is that we can heat things up with sound, which I think is pretty cool. And I'll be happy with that effect. Leave it at that.
Cool. So if I yell at you loud enough, you'll start glowing? Is that the takeaway?
I guess it's kind of like the you can slap the chicken breast and cook it problem, but you can yell at the chicken breast and cook it now. Yeah.
Cool. Doris, it says, when did you know you wanted this to be your career? Who or what inspired you to dive into this?
Okay, this is a very personal question. Okay, so I got into my research area knowing I want to do research with social identity. So it's basically the idea of how you define yourself and kind of form your beliefs and behaviors based on your membership in a group. And I luckily started working with my advisor, Dr. Stephanie Freiberg, but I didn't intend to study Native American because I spent most of my life in New York State and Ohio, which I didn't have any contact with Native Americans. To be honest, I'm very ashamed of that. But so at first, I was kind of resistant when my team was trying to get me involved in the research because I was like, I didn't know about this group. Why do I want to spend so much effort and time? But as I read more and more about this group, and I started realizing why I didn't know about this group, why I didn't care about this group. That's the moment I realized, well, the reason exactly why I didn't care about this group is exactly why I need to study this group, because it's not like a standalone problem just happened to me. It happened to most of us. So yeah, that's how I started my passion.
Awesome, thank you. And then this is going back to Lance. It says, can you give an order of magnitude estimate of how much less chemo would be needed using the successful ultrasound treatment, and what this might practically mean for patients?
I have no idea. That's part of the research, I guess. That's the exciting part. Yeah, this topic of research is kind of in its infancy, I guess. It's been a growing field now that people have discovered that you can enhance drug delivery with ultrasound, specifically with chemo. That kind of touches on the question I had previously where we don't really understand why things are happening and why we're fully uptaking drug. All I know is that we can expect slightly less chemo to be used, but hopefully I can figure it out soon.
Great. And then going back to April here, it says, are there examples of therapies that can target specific genetic changes already, or is that still a goal that we haven't reached yet?
There are therapies, and some are for cancers, for different, including lung cancers, for specific gene changes, and ones that are particular to splicing are more in the early stages, but they do exist for some developmental diseases. So we can expect that these will be moving faster into the clinic in the coming years.
Cool. And then back to Lance here. When did you initially think of this idea using microbubbles in ultrasound? What did the people around you think?
Well, my advisor who gave me the idea really liked it, so I guess there's that. Microbubbles have been around for a while. I alluded to it that they're a contrast agent. They make the pictures better. That's kind of how they got their start, and they've been used for a couple decades now, actually, but in the US, they're not really used. It's not widely accepted, so part of me giving this presentation is spreading the gospel that microbubbles are safe and effective for, at the very least, improving your imaging quality. But now we're starting to mess around with, I guess, the weird parts of microbubbles that you can cause temperature rise and poke holes in things and fun stuff like that. So that's more recent. I'd say, I guess, maybe a decade or two of messing with microbubbles in that way, specifically with enhancing drug delivery, but not my idea. I can't take credit for it, but I'm having fun messing around with all that.
Sure. And then I've got two final questions here, one for Doris and one for April. So for Doris, what class or subject helped you the most when starting in this field? And what advice can you give to aspiring students in college or high school that want to get involved?
I don't know if I'm able to ask a clarification question. I guess I'm just curious, by in this field, do you mean psychology in general? Do you mean social psychology? Do you mean indigenous studies? Because I'm kind of interdisciplinary here.
So it's anonymous, but if anybody asks this question and
I
wants
don't
to
know
clarify.
if someone asks the question, can do a follow-up.
Or just answer whatever one you want to answer.
Okay, I'll just assume it's social psychology then, since it's my passion. So let's see. Sorry, can you repeat the question very quickly?
No, because it went away.
Oh, okay. So I think it asks about advice at school.
Yeah, like what
right.
ways can someone in high school or college take to get involved in this field if they're interested in it?
Okay, so not just courses. Well, if you want to get into doing psychology research, I think the best way is to volunteer to work at a lab, especially if you are in a college. Even if you are in high school, you can reach out to like nearby college and find their lab and ask the supervisor saying you're interested and can you get involved and you're willing to work like, well, say you're willing to volunteer, and usually they are happy to take on volunteers. And while you're in college, be very involved in the department and just sign up for lab classes, and also, again, email the supervisors to ask if you can be a research assistant. And so that can kind of give you a better sense of what research is. Are you actually interested in doing research? And also, it becomes a really good line on your resume when you apply for grad school or when you apply for a professional research job. Yeah.
Wonderful, thank you. And then our final question of the night for April, and it's how did you start in your field and what has been the most challenging thing in your journey?
So I got really lucky back in high school when I took AP biology and my teacher was like, you seem really interested in this stuff. There's an opportunity to do summer research in a lab, and I really enjoyed that. But a story I like to tell is that I spent a lot of that summer just kind of counting cell colonies in like dozens of plates, and I was like, this isn't really what I want to do. So I have instead learned how to like do more coding and programming and data analysis so that I can do that kind of counting, but like with a computer so that it's less just kind of time-consuming menial tasks. And so learning all those computing skills alongside also learning the biology has been a lot, so that's probably what I would say is the main challenge.
Wonderful. Thank you so much, April. And thank you all for submitting so many questions. It was great to see so much engagement today. And let's give one final round of applause to our speakers for tonight. And this is the final event of our Engage seminar series for this spring quarter. So if you liked what you saw, be sure to join us next year when we'll have this series again. And if you want to learn more about the Engage program, again, this is a program at University of Washington run by grad students to train other grad students in how to communicate science to the public, just like we've done here tonight. If you want to learn more about our program, please visit us on the web at engage-science.space. Or check us out on social media at Engage Science. And with that, that's all we have for you tonight. Thank you all for coming, and have a great rest of your evening.